Oh, sure. Yes. We switched to English. Well, okay. Thank you very much. Maybe I can introduce it formally if it's correct. Cool.
Yeah, sure.
So, welcome, Paula, to our seminar series. And it's a super pleasure, like, by organizing this seminar. And, like, after I invited you for, like, I invited you, I think, a month and a half ago. And all of a sudden, wow, you joined us. So I'm extremely happy. And I guess this is usually not the case, that I invite someone and then someone join us. But I'm super happy to introduce Paula Garcia Molina, which is a doctor in physics and recently incorporated in our quantum machine learning group in the Computer Vision Center. And it's really a pleasure to have you here. Today we'll talk us about quantum computing and quantum-inspired numerical methods. And I like to say the floor is yours.
Thank you for this kind introduction. As Matthias said, my name is Paula. I am now, like since last week, a postdoc researcher at the Computer Vision Center. Today I'm here to talk about the research that I did during my PhD thesis, which is quantum computing and quantum-inspired numerical methods, which was done under the supervision of Professor Juan José Garcia Ripoll at the Quantum Information and Foundations Group of the Institute of Fundamental Physics at Spanish CSIC Research Institution. So I would like to say before starting that this topic could be quite harsh. So the main idea here is that you understand why this is interesting, which kind of things we could do with these new techniques. So if you have any doubts, please interrupt me. So I think this way it's easier to understand everything. So during this presentation, I will follow this outline. First, I will motivate the need for new, more efficient methods for solving partial differential equations, or PDEs. Then, I address the solution of these static PDEs using quantum algorithms, and afterwards, quantum-inspired alternatives for solving both static and time-dependent PDEs. Finally, I will perform a summary of the results, the conclusions, and the outlook of this research that I did during this thesis. So now let's start with the motivation. High-performance computing, or HPC, tackles some of the most demanding computational challenges nowadays. And many of these problems require further simulation of physical phenomena, with partial differential equation at the core of such models. Indeed, here we have a plot that describes the HPC use of applications of one of the top 10 supercomputers, which is the Leonardo HPC. Here we observe that some fields, such as condensed matter physics or computational fluid dynamics, are those with a higher percentage, and these are dominated by this kind of equations for solving their problems. Here we can observe some examples that show how important these PDEs are in real-world applications. For example, we have nonlinear PDEs, such as the Navier-Stokes equation, that is of use in fluid dynamics, and also other proposals, such as this heat conduction equation, a linear equation that is very important in the field of nuclear physics. Indeed, physics is one of the areas in which PDEs play a more prevalent role, with interesting applications in the emerging field of quantum technologies. Here we see the time-independent Schrödinger equation, which is the following one, and this is now very useful for the simulation of superconducting qubits, which is one of the main proposals for the development of real-world quantum computers. The solution of this Hamiltonian PDE will output the energy levels of such qubits. And then its simulation is very important before the fabrication of these devices to understand how they will behave in practical situations. However, this is something that is becoming more and more complex as the number of qubits increases. And for the case of matrix diagonalization, based on the standard vector approach, we are overcoming the memory limitations of these techniques. These kind of challenges can also be found in the realm of time-dependent PDEs, such as now this Schrödinger equation that is very important in the area of quantum physics or quantum mechanics, since it describes how a quantum system evolves. Here we show just one example in which this equation could be of use, which is in the field of levitodynamics that studies the behavior of particles that are levitated in vacuum. Here what we can see is that in this field we will have a particle that is initially in a ground state, so at equilibrium, and there is a sudden change in the potential of the particle that leads to a new state that is going to be modeled by this Schrödinger equation. While obtaining this new state, there is going to be a widening of this potential, and therefore we will need a very high resolution to capture the behavior or the solution of this PDE. And this will increase the memory requirements, again overcoming the possibilities of standard PDE solvers. These kind of challenges also arise in more general PDEs, such as, for example, the heat or the wave equation that we can see in this plot. So here what we see is the scaling of the runtime with a number of points necessary for solving the PDE, which is in fact associated with the memory requirements. So, for example, if we want to solve a PDE with around 10 to the 9 points for the three-dimensional case, it would mean 1,000 points per dimension, which is in fact not a lot. This will render 2 weeks in time and the use of a standard laptop in terms of memory. However, if we go further, for example, to this extreme, this would take centuries in order to achieve that. And this is only in the case that is possible, which is in fact not possible because even when using high-performance computing, the memory is not enough to solve these kind of problems. So here what we are observing is that now we have two challenges, which are the memory and the computational cost that are just too high in order to solve these kind of problems with the state-of-the-art vector-based PDE solvers. So then there is a need to develop more efficient solvers for PDEs, and in this context, that is what we propose with this thesis that I developed, which is to now create new quantum and quantum-inspired algorithms for numerical analysis, focusing on the solution of partial differential equations with significant memory compression and time savings while maintaining a high accuracy. When obtaining these methods, they will enable us not only to overcome this limitation of these standard PDE solvers, but also to make them more efficient, which will reduce the needs in terms of memory and energy, and consequently the economic impact of these kind of techniques. So after this introduction, I will now focus on the first part of my thesis, which was the development of quantum algorithms for numerical analysis. So, quantum computers offer an exponential advantage in both the information and processing of information due to the use of the superposition principle, together with relevant speedups in algorithms such as the quantum Fourier transform. So, this kind of advantages that were observed in quantum computers motivated its application to the field of numerical analysis, leading to a new area that is known as quantum numerical analysis, that uses this kind of computers for solving problems such as interpolation, system of equations, or partial differential equations, which is the one that we are more interested in. This is very interesting because these PDEs suffer from the same exponential complexity as quantum computers themselves. So this is what motivated sort of the first works in this area, in which they resort to fault-tolerant quantum computers to design their algorithms. Here we have just some examples, which could be based on quantum amplitude estimation, or the Harder-Hessedin-Lloyd or HHL algorithm for the solution of system of equations, which with different kinds of PDEs have been solved, such as, for example, the wave equation, the heat equation, or the Poisson one. However, there is a problem with these kind of proposals, and it is that they are designed for fault-tolerant quantum computers. And sadly, nowadays, we are still not there yet. In fact, we find ourselves in the noisy intermediate scale quantum era, or NISQ era, that is characterized by quantum computers with a limited number of low-performance qubits or noisy qubits, but it's not enough to apply quantum error correction at a large scale. What this means is that current devices are dominated by the effect of noise, and this leads to errors in the computations. So if we want to implement the Fortran algorithms that we had before, we will need thousands of logical qubits with a very high performance, and this is simply out of our scope nowadays. However, there is a possibility in order to take advantage of these devices, and it is to rely on variational quantum algorithms that combine the use of a quantum and a classical computer in order to make the most of them. With these proposals, we have already observed that they are more suitable to this state of the art because they have lower hardware requirements as well as a higher noise resilience. And this is obtained by following this kind of a scheme in which the quantum computer encodes the parameters of our model in a way similar of the case of a neural network. And this is done using a parameterized quantum circuit. Then this circuit is measured, and the result of the measurements are used as the cost function of a classical optimizer that in a classical computer finds the new optimum parameters, and this is performed until convergence, in which we have the solution encoded in the quantum circuit. This algorithm, which is originally known as the variational quantum eigensolver, was developed for the computation of the ground states of Hamiltonians in quantum chemistry, but it was soon extended to other applications, such as the ones for solving partial differential equations. And here I just show you some different techniques that could be used to solve each of the parts of the algorithms for solving these kind of problems. So if you want to solve a PDE in a quantum device, the first thing is how to encode this problem in a quantum computer. And for that, we use amplitude encoding, or this is the most standard technique, for representing the function in the amplitudes of the quantum states. Then, for the codification of the PDE itself, the operator, the most standard alternative is the finite different method. Once this is done, it is necessary to propose a variational ansatz to represent this problem, and it is standard to use hardware efficient ansatz because they are designed to maximize the accuracy in the certain coupling of the device of our choice. Then the cost of function that will depend on the PDE to solve, and the optimizer that it is standard for it to be stochastic due to the intrinsic probabilistic nature of quantum computers. So with this, a lot of PDEs have been successfully solved with a variety of techniques, and this motivated us to create our own proposal. And this led to this paper, which is a quantum free analysis for multivariate functions and applications to a class of Schrödinger type partial differential equations, in which we created a variational quantum algorithm for solving Hamiltonian PDEs with a new Fourier-based encoding, as well as ansatz for the representation of functions and their symmetries. So in order to do that, as I said, regardless of if we have a fault-tolerant or a NISQ device, it is necessary to find an efficient encoding of the function in a quantum register. And for that, we propose to resort to Fourier analysis. So the first thing is to discretize the position space into 2 to the n points that correspond to the 2 to the n states of an n-qubit quantum register. And once we have this discretized space, we can map a function to the n-qubit normalized states that we have here, in which each of the amplitudes of our state encodes the corresponding value of the function for the associated coordinate, using this binary representation. When doing this, what we have is in fact the previous amplitude encoding applied for the representation of functions. And if we now use the Fourier transform, it is also possible to move from the position space to the momentum space. And this is the basis of this codification that we propose. To understand this better, I have here an example of how to represent a Gaussian function. So the idea is that now we want to represent this function using 2 qubits. That would mean that we will have 2 to the 2, so 4 points for the representation of the function in the amplitudes of this state. So as we can see here, there are 4 values of the coordinates and 4 associated values of the function, and each of them is stored in the amplitudes of the corresponding state of the register using this binary correspondence. when you represent this function in this graphical form, what you see is that the more qubits you have, the more points, and then the more accurate approximation of the exact continuous function. A very interesting thing here is also that it's possible to use the non-equidistant theorem to determine the minimum number of qubits that we need to represent this function. And with the Fourier interpolation, we can recover it in the limit of the continuous function with an error that decays up to double exponentially with the number of qubits. Additionally to this representation
Paula,
of
I'm sorry. Can I? Do you mind? I'm super sorry to interrupt you. I got a bit lost. So you have some sort of two-dimensional grid in which you have LX points for the. This I got super lost. So you have what is LP? What is LP?
LP. Oh, okay. No. So the idea is that you have a one-dimensional function, this one.
Mm-hmm.
So one-dimensional is because it only depends on x. So
yes.
you only have a grid on x. LP is the grid in momentum space.
But in principle, so, should be the same as LX, no?
So it's not the same because the definition, the definition points are not the same. But the number of points, it is the same.
Okay. I get it. Yes, nice. Sorry to interrupt you.
No, it's fine. Don't worry. So as I was saying, this representation of functions can also be extended to operators, and this is very relevant because we need to represent operators if we want to solve partial differential equations. And for that, we use a quantum representation of the operators, concretely this Hamiltonian operator. A Hamiltonian, which is an object very useful in quantum physics, has two distinct elements, which is a potential, which is this one, and also a differential operator. So in the case of the potential, this is in fact, in terms of matrices, just a diagonal matrix, so it can be assimilated to a vector and represented using the same codification as we just showed for functions. But in the case of the differential operator, we need to use methods that are capable of approximating the derivatives, as it is standard in numerical analysis. And what we propose here is to use the spectral method that uses the Fourier transform and its inverse to compute the derivative in momentum space. However, as I said, it is more common in standard applications to use the finite difference method that approximates this derivative as a weighted sum of displacement operators. But even though these methods are easier to implement, they have an error that scales exponentially worse than the one of the spectral method. And in this context, in which we have a limited number of qubits, which are noisy, it is better then to rely on this spectral technique. Once this representation has been presented, I wanted to show you the quantum circuits that we use for this implementation. And the first thing is the ansatz for the representation of the problem as a variational quantum circuit, which is known as the CGR ansatz. This one was introduced by us, inspired by the one proposed by Salka, Grover, and Rudolph. And this is specifically designed for the representation of functions in a quantum circuit by applying conditional rotations, as we can see here. With this, we can have a highly efficient representation of smooth functions, but the number of parameters scales exponentially with the number of qubits, which makes this very costly. So to reduce this cost, we propose to use a circuit that is capable of doing a symmetrization of the function, which means that if we have a function that has reflection symmetry, we just encode in the variational circuit the right part of the one that corresponds to the positive part of the function, and then its source of copies the other part. So this way we can reduce the number of parameters. And additionally, we also introduce Fourier interpolation algorithms that, without increasing the number of parameters, are capable of increasing the number of points and having a finer representation of these continuous functions. So with all these ingredients, we are now ready to describe our variational quantum algorithm, which is the variational quantum PDE solver that addresses this kind of Hamiltonian equations. In this equation, the goal is now to obtain the minimum energy. So this is equivalent to the ionization problem, in which you want to have the minimum eigenvalue. And this, in terms of physics, would be equivalent to having the ground state of this problem. So now what we have done is to transform the problem of the solution of a PDE into one that admits a variational formalism and can be solved with this variational scheme. And this is very similar to the one that I just introduced in the motivation, but now applied for the differential equation. So here what we have is two quantum circuits that encode the function in position and momentum space as variational parameterized circuits. Then these are measured, as we can see here, and obtain the approximation of the potential and differential operators for the expectation value. These values are used for the estimation of the energy, which is the cost function of the classical optimizer, and this is iteratively repeated until convergence, for which we will have the solution of the PDE represented by this quantum circuit. And now I just wanted to show you the results on how we tested this kind of proposal. So here what we use is a very simple benchmark equation, which is the Schrödinger equation, applied to the quantum harmonic oscillator, which is one of the quintessential models in quantum mechanics. Here the solution is the ground state, which is a Gaussian one, and this is very well suited for what the kind of circuits that we develop. So in order to now compare the results and see how well the performance is, we have two figures of merit, which are the continuous fidelity and the energy relative error. Regarding this fidelity, it determines how well we can recover the exact continuous function for the one that we obtain from our variational algorithm. And then, in order to measure other properties of the solution, we will also address the energy relative error regarding the energy of the ground state that we recover. So, using these metrics, we have the following results. In this work, we first decided to determine the optimum optimizer and ansatz using an ideal simulation of the quantum computer, meaning that we will have no noise sources. For this, we use the continuous infidelity, so the lower the better, and this energy error that we just introduced. So regarding the optimizer, what we observe is that the best performance is achieved by the Adam one, and this is because it uses an analytic estimate of the cost function gradient. And in terms of the ansatz, also the best performance. So I wanted to say first that we introduced two new ansatz, which are the real amplitudes one with depths 1 and 2. This ansatz is quite standard in quantum machine learning because it searches the whole Hilbert space, so it's a very general purpose ansatz. And it also has a scale of the number of parameters that is linear with the number of qubits, making it very interesting for practical applications. However, as we can see for this concrete application, the performance of the ZGR, which was designed for the representation of functions, is much better. And in the case of the RY, or real amplitude ansatz, as the number of qubits and then parameters increases, it gets trapped in local minima, showing a more chaotic nature. So what we can see is that the best performance is Adam combined with the state GR. If we want now to improve on this performance, it is necessary to perform more circuit measurements. And if we go to and this will increase the accuracy of the energy error and then also of the approximation of the solution. If we now go to the infinite number of measurements limits, what we see is that we can decrease this error up to 10 to the minus 9. And this is something very relevant because it shows that our proposal, our representation based on the Fourier techniques, is very efficient and accurate. And what limits this is the number of measurements that we can, in fact, perform. So to end this quantum machine learning section, I wanted to say that if we want to really know how well this will perform in real devices, we also need to consider the effect of noise sources. And we also did this using a simulator of a real device, combined with the ansatz and the optimizer that we expect to perform better because of the stochastic nature of the optimizer, the SPSA, and the smaller number of quantum gates of the RY with depth 1. In fact, when we perform the simulations, we observed that as the number of qubits increases, this noise affects the fidelity, which decreases. And it is expected because we have more quantum gates and associated noises of their application, as well as an error according to the decoherence. However, we can still obtain significantly low infidelities, and the real effect is caused in terms of the energy error, which is now much higher. However, we can also address this using this an error mitigation techniques, which is the zero noise extrapolation for the thermal relaxation channel. And when using this, we observed that by a Richardson extrapolation, for state-of-the-art values of the thermal relaxation time, we can still recover a considerably good error of this energy. However, there is an issue with that, and it is that this error mitigation technique, even when successfully applied for this reduced scenario, it cannot be scaled to larger number of qubits, and we have also observed that even in the infinite number of measurement limits, the results obtained do not match the accuracy of more standard classical methods. So, after having observed that, we can conclude that these noise and quantum fluctuations limit the efficiency of our proposed quantum register encoding, and what would be interesting now is to see if we could take advantage of this kind of efficient techniques in another context. And in fact, this is possible, and this is what we did, by using quantum-inspired algorithms based on the use of tensor networks, which have already shown some heuristical advantages for solving these kind of problems. And with this, we go to the second part of this talk, in which we now address the quantum-inspired solution of partial differential equations. So now I wanted to stop to see if you want to ask anything, or if not, I will continue.
I have some questions, but if someone else in the audience has, super welcome. Okay, otherwise, I want to ask you, like, so you have the quantum harmonic oscillator, no?
Yeah, sure.
And then you encode you encode p square with the Fourier transform, and then x you said you have a displacement operator.
Mm-hmm.
Beyond all this, what I wonder is, first, from the result part, you evolve this from a given initial state, or using the continuous fidelity, this is averaged? No, I mean, you start, which is like the initial state, and that how do you initial?
Yeah, so in this case, since we know that the form of the solution is going to be Gaussian-like, what we do is to load a Gaussian function as the initial starting point, and this will evolve to the final solution. But this is because in this case we already know what to expect.
But this is the ground state, no? Yes, okay, it's a ground state. Yeah, it says there.
Yeah.
Okay.
But this also works with others. So this, in fact, in the original work, this was tried with different quantum circuits. So the idea was to simulate different qubits. We also tried, for example, a flux qubit in which the solution is not like this. It's not a Gaussian. It has a well in the middle. And even if you start with a Gaussian-like form, it will also converge and find the well structure.
Let me check.
So this is just a way of accelerating the calculus, because you, in this case, now the form more or less that you should expect. This is common in a lot of applications. In this kind of numerical analysis, that you have some sort of intuition of how your function is going to behave.
Super, super cool. Wow. It's impressive. Sorry, for me, it's okay if we go on later, we can. But if someone else has questions. Okay.
Okay, I will continue now. So in this second part, I will now address the quantum inspired solution of.
Sorry.
Yeah.
Yeah, hands on. No, just curious because you speaking about Fourier-based method, you use it for the spectral decomposition. Is it right? Have you never tried something else? Or as of now, just curious, don't worry, it's an open question, just curiosity. Have you ever tried some other type of discretized Fourier or?
Yeah, but for the application of derivatives.
Okay.
Yeah, because in this context, Fourier was used for two things, either for the approximation of the differential operator or also for the interpolation, because we also perform an interpolation to approximate it to a continuous limit. So in the case of in the results that I will present now, that are for quantum inspired techniques, we tried other interpolation techniques, which are based on finite differences. And regarding the differential operator, we also use the standard finite differences, but we also introduced a new technique for approximating derivatives. That is the oscillator spectral one. It's called the Hermite distribute approximated functional, which is already known in numerical analysis, but we extended it to quantum inspired techniques. I will speak about this later.
Okay, thank you.
Yeah, you're welcome. So regarding this quantum inspired part, these are algorithms that are in fact classical, but in some sort of way emulate quantum phenomena, so they can obtain speedups with respect to more standard classical algorithms. In this case, our quantum inspired algorithms are going to be based on the use of tensor networks. This is a mathematical formalism for the representation of quantum states, and it is typically used in the area of quantum many-body system to represent quantum states of this form, in which we have m d-level particles, which is in the standard wave function representation would be a vector that has an exponential scaling of the number of parameters with the number of particles. And in this context, when you represent this vector as this kind of tensor, it is possible to rewrite this as a tensor network, and this will enable us, under the correct circumstances of entanglement, to have a polynomial scaling. So when we do this is, okay, instead of exploring the whole Hilbert space with our system, since we do not really need in practice all of this configuration, we are going just to be restricted to these ones, and this will be assessed by this Arial law of states. So this is how this works in this setting in quantum physics, but we are going to see how this could be applied to numerical analysis, and these kind of things could also be applied to machine learning, and it is in fact one promising field nowadays. So I just wanted to introduce to you a little bit more how this works, but so the real details of how this behaves and how to work with this are kind of difficult to grasp, but here I just wanted for you to have like an idea or an intuitive idea. So these kind of tensor networks are typically represented using this diagrammatic notation, in which a tensor is just a shape, and these lines, which are called legs, that come out of it, are going to represent the indices of our tensor. So for example, this would be a rank 2 tensor, which is a matrix. And when we now want to represent a matrix multiplication, such as this one, this would be equivalent to this diagrammatic representation. And this is something super powerful, because in this context, we are going to have to contract a lot of tensors. So it is much easier to represent this just in this way. So here are just some examples of tensor networks, but in practical applications for us, we are going just to focus on this one-dimensional tensor network, which is known as matrix product state, or MPS. To understand a little bit better how this works, we see that each of the elements of the MPS is a rank 3 tensor, and it has 3 distinct legs. So this one is known as the physical index, and it accounts for the physical dimension in the case of a particle. And we will see that it will account for the coordinates in the function representation. And these others are indices that are now spiritual or Bohr indices that arise from the deconstruction of this big tensor into a set of small and interconnected tensors. And this is something crucial because this maximum value of the rank of these tensors, which is known as the bond dimension, is the one that is going to limit the entropy of the entanglement of our network, and this will in turn assess the cost of the contraction, which is the most costly or the costlier operation that we will be dealing with when using this kind of formalism. And similarly, we can also represent, so if MPS were for the representation of quantum states, which would be equivalent to vectors, the matrix product operator is for the representation of quantum operators, which are typically represented as a matrix. And in this case, we have a rank 4 tensor because we need to contract this with the MPS. So when we apply an MPO to an MPS, we will also have now an MPS. And now let us move on to the functional encoding with this kind of formalism. Up to now, we have focused on an encoding that was designed for a quantum register, but these kind of tensor networks are also amenable for this representation. And there is a very easy mapping, that is to map the qubits of our register to the tensor, also known as sites, of our MPS. And when doing that, we can encode an exponentially large number of points in the number of qubits or tensors of the MPS. And this is something that is very advantageous, because if the bond dimension that interconnects these tensors scales polynomially with the number of tensors of our network, we are going to have an exponential advantage for the representation of functions with respect to the standard vector notation. This is something that can also be extended as it was before for the representation of operators, and in the case of potential, it is done using matrix product states or MPS. Here we see how some very relevant potentials can be represented with a very reduced bond dimension, and in other cases that are more complex, there is an algorithm, that is the TT cross interpolation, that can be used for general potentials. Additionally, in the case of the differential operator, we now resort to the MPO that we just presented, and with this we can approximate the different techniques such as the finite different or the spectral method, that since it is more precise, it's also costlier. So with these ingredients, the MPS for the representation of functions and the MPOs for operators, we can create an algebra that is equivalent to the one of matrices and vectors. And here we just show some operations. For example, this MPS multiplication would be this contraction, and is equivalent to the element-wise vector multiplication. Or here we have this MPO-MPS multiplication, which would be matrix vector multiplication or the scalar product. The thing is that in practice, if we perform this just like this operation, these contractions, we will obtain the same solution that we could with vector matrices. And if we do that, there will be no advantage because we will still have the same number of parameters and no memory compression. So in practical applications, what people do when working with tensor networks is to perform simplification or a reduction of this bond dimension that will enable us to have this memory compression, but at the same time, even though we have now a finite precision limited by this, we will see how the accuracy is still very high and similar to the one obtained with the standard methods. So with this, what we do is to create now an algebra for the application of quantum-inspired methods based on tensor networks, more concretely on MPS, to numerical analysis. And here, well, I just show some of the approaches that people have been using during the last years. And this is something that is very curious, but it happens actually a lot. And it is that this kind of tensor networks were discovered like in two fields without them knowing of each other. So in the case of physics, it was developed for these quantum many-body systems, which suffer from the same exponential complexity of the Curse dimensionality as these PDEs. But in mathematics, independently, they also develop a formalism that shows the same compression, that is the one of tensor trains, that is in its quantized version. It is exactly equivalent to the representation of functions using MPS. So now people are aware of this, but I mean, throughout the years, there has been like a parallel development of these areas. And for example, in terms of the algorithms in physics, they typically use the density matrix renormalization group algorithm applied for the solution of PDEs, even though this is a ground state search algorithm. And in mathematics, they have the alternative least squares, which is basically the same as DMRG, but now applied for the minimization of the residual of the system of equations that is associated to the PDE. So all of this work motivated us to use our MPS-MPO finite precision algebra to develop new global methods for general PDEs represented with non-local MPOs. And this is something that is key here, is that the methods that we create are global. And this means that all the tensors of the network are updated simultaneously. And this is something very uncommon because these more standard DMRG or ALS methods use a local optimization in which at each iteration, just one of the tensors is updated. And this leads us to the first work that we developed in this quantum-inspired context, in which we address now the same type of static Schrödinger type Hamiltonian PDEs, but using this finite precision algebra, relying instead of on Fourier techniques on the most standard finite different approximation, and using a variational truncation of the tensor network of the MPS that will enable us to optimize the bond dimension according to a certain prescribed error. So, well, here is just the same function, the same PDE as we had before, but with the difference that we can go to the two-dimensional case thanks to this memory reduction of the tensor networks. And we see that here is again a quantum harmonic oscillator, but now it is a squeeze, meaning that we have correlation among the variables, and also that this is no longer symmetric, this Gaussian solution, but it is also, it shows this squeezing, and we choose this also to be rotated for it to be more complex to solve. So in order to obtain this solution, we propose a series of algorithms that are adaptations of standard algorithms in numerical analysis to the field of tensor networks. So I want you to have more or less like the idea of how this works, because these algorithms can be quite harsh, but it is interesting to know that this exists and how this can be applied in this context. So the first proposal is the use of imaginary time evolution. And what this does is, in the Schrödinger equation that we are aiming to solve, is substitute the time by an imaginary time, transforming the solution in a way that in the infinite imaginary time limit, it approximates the current state. That is the thing that we are looking for. So the most standard methods are known as Runge-Kutta or splitting methods that are based on the use of the Taylor expansion. And here we have the simple one, which is the Euler method, although there are much more, as we can see here. However, there is an issue with this kind of methods, and it is that we need to find what is the optimal step size that we need to perform, and this can be very costly. And moreover, they can be, if we choose this incorrectly, very unstable. Also, they do not exactly target this ground state because they are not designed for this transit search. So in this context, what we propose is to use other kind of algorithms which are approximate diagonalization, which do in fact perform a global optimization of our problem by directly minimizing the energy, which acts as the cost function of the problem. So the algorithm that is more interesting to us is this Arnoldi iteration. This is an algorithm that is widely used nowadays for matrix diagonalization. In fact, this is the one behind all the diagonalization routines in very relevant libraries such as CPy or NumPy. So what we do here is to adapt this to this formalism of MPS. This algorithm works in the following way, in which you have a Krylov subspace, which is defined like this by successive applications of the Hamiltonian onto a trial state. And you can rewrite your problem in this subspace. And now in the end, this iteration is going to be reduced to the solution of this reduced dimensional system of equations or eigenvalue problem, in which the dimensions are going to be given by the number of Krylov vectors that you are going to choose. And in practical applications, you are going just to need 5 or 10. So you really have an exponential decrease in the dimensions of the problem or the matrix that you need to diagonalize. And other methods that are of this type, more of approximate generalization, would be the well-known gradient descent, which is in fact an Arnold iteration just for 2 vectors of the Krylov space, and the power iteration. Besides these methods that are global optimization ones, we also introduced the density matrix normalization group that, as I said, is very standard in this quantum-inspired community. In this case, a local minimization of the tensors is performed, so one tensor is fixed and the others, so all the tensors are fixed except one, and this one is going to be optimized by solving this eigenvalue equation at each step. Then this tensor is updated, and we repeat this until convergence, performing sweeps throughout all the MPS back and forward. So now that we have presented all these methods, I just wanted to show you so a benchmark of how they perform. These are all based on the MPS formalism, and what we see is that DMRG in this when we observe the cost scaling, which is going to be the runtime to achieve a certain error in the energy, with the number of qubits, which is a measure that is logarithmic in the number of grid points of our solution, what we observe is that the DMRG in this case, because this is very simple Hamiltonian with low entanglement, performs very good, much better than all the global optimization algorithms. And among the different global optimization algorithms, we also see that this kind of Arnold iteration or gradient descent based are the ones that show a better performance. And this is something expected because here for these Runge-Kutta ones, we are not including the cost of finding the optimum step. And if we did, all of these will increase around 1 order of magnitude. So this makes us neglect them. And for the practical applications of more complex problems that I'm going to show, we will just retain the Arnold iteration or the DMRG because they have the best performance. So now this is the solution of the 2-dimensional PDE for the quantum harmonic oscillator. And now we are going to introduce the effect of this MPS, besides this MPS Arnoldi and DMRG, we also will be using vector-based Arnoldi, which, as I said, it is also used in libraries such as RPact or Prime, which is a very optimal library for matrix diagonalization. So here, what we are showing is the relative runtime of the methods for obtaining the solution of this PDE as it at the number of qubits per dimension scales. So this is going to be up to 2 to the 28 times 2 to the 28th matrix, because we're going to have 2 dimensions, so 14 qubits per dimension, 28. So here what we observe are 2 things. First, regarding the MPS methods, which are the DMRG and this MPS Arnoldi base, there is a better asymptotic scaling, since we will see how this runtime scales exponentially for the vector case following this higher tendency. However, when we compare the DMRG with our proposal for this global optimization, we see that DMRG has a better performance. And this is because here we have not considered the fact that DMRG performs a renormalization. It is a renormalization group algorithm, which is sort of a kind of interpolation. So if we now introduce an interpolation in our Arnoldi proposal, it is possible to obtain the solutions for all the different grids. And here we can compare the results in terms of the energy error for the vector and MPS-based methods. What is very interesting here is that we have very similar precisions or accuracies, both for MPS and vector approaches. But when it comes to the memory, we see that the vector methods have an exponential memory scaling, while the MPS-based ones have a memory that now in the end stabilizes. So there is an exponential memory compression when using MPS for solving these kind of equations with respect to the standard vector-based methods. And in this case, we can even obtain the same accuracy. So this is a huge advantage that we have found. And something that we see here is that, in fact, there is this stabilization of the memory, and this is something related to the problem that we are solving, in which the solution is a Gaussian. And at some point, even though we are adding more points to our representation, it is not necessary to increase the bond dimension because we already have all the information that we need. And this is something that was later demonstrated by Jobs and collaborators here, in which they see that if you have a function that has a fast decaying Fourier spectra, such as the Gaussian, it has also a bounded bond dimension, which is what we see in these results. So I'm going just to briefly highlight some of the themes of this other paper, because the main results are more or less the same, and this is some more about the physics. So if you are interested, I mean, we could talk another day, but I think it's just worth highlighting some of the differences rather than explaining in detail the physics behind this kind of experiments. So in this second work, what we saw is that these huge advantages in memory, especially, and also in runtime for some applications, could be also worth trying in a more complex PDE, which is the solution of the time-dependent Schrödinger PDE. And here in this work, we will see that we observe the same kind of advantages in memory, but we also introduce a new thing, and this is what they ask, and I'm going to show briefly, for approximating a technique for approximating derivatives. Here is just the problem that we are solving, which is again a harmonic potential, but it is the one that I mentioned in levitodynamics, in which there is a change in the potential, and then you have to simulate this through the Schrödinger equation. So the thing that is more important in this work is that we introduce a new technique for the approximation of derivatives. And this is super important because up to now, there had been two main alternatives, which is to use the finite different approach, which is easy, but the error scaling is not very good, or the Fourier one, which has a very good error scaling, but can also be very costly. So with this kind of proposal, which is to use Hermite distributed approximating functionals, or HDAF, we have a pseudo-spectral accuracy, but with a cost that is very similar to the one of the finite different approximation. And this can be done using this kind of kernel for approximating the derivatives, which is a sum of Hermite polynomials weighted by a certain Gaussian. So it has a series of parameters that can be heuristically tuned. And with this, we can approximate functions, derivatives, and functions thereof, such as, for example, the propagator that is useful in an evolution problem such as this one. And this can be done using this weighted sum of displacement operators, which is in fact very similar to the one of these finite difference. So I think this is the most relevant thing introduced here. Well, we also studied this time-dependent Schrödinger equation, as I said. And besides the previous algorithms, we introduced one that is very standard, which is the split-step method. And this split-step method is just, instead of applying the whole exponential, you approximate this by different smaller operators. And this operator, which is here, the differential operator, can be approximated with the HDAF that I just introduced. This other that is more complex is also a potential, but can now be approximated with this TT cross interpolation that I mentioned. So this is an existing technique, and this is becoming more and more popular nowadays because it has many applications and it's very, very accurate. So just to show you more or less like some of the results that I think they are more interesting for you here. This is just a benchmark in which we studied like a 100-fold expansion. So the initial Gaussian function expands like 100 times, so we need a very high resolution to capture it. So here what we see is the same kind of errors. The same kind of, not errors, sorry, the algorithms for evolution. And here is the error scaling with the step size that we choose for performing this evolution, because we are simulating a time evolution. So what we see is that the error scaling in case of the finite difference for a fixed number of qubits, which means that we are fixing the grid size, is in fact limited by the error of this finite difference. We cannot go lower than here, and this is because of the grid size that we have. But in the case of the HDAF, for the same grid size, we can obtain much better accuracies. And here in this right part, these both scale as predicted by theory, but as we go to smaller time steps, the errors of the discretization dominate. Here, they really leads to a high error, but in the case of the HDAF, we can achieve errors that are close to machine precision, and in practical applications, we see that are the same that we could obtain using standard vector approximations, even though we are using MPS, for which we have this memory expression. And for one of the methods, that is the best performing one, which is the split step, we compare this for with vector fast Fourier transform approximation, which is like the more standard split step technique. And when comparing the performance of these vectors and MPS, we observe that using MPS, which are these color lines, these are different precisions for truncation. So, but what we mean is that if we have a sufficiently good truncation, we can obtain the same accuracy using the MPS as vectors, which is in fact the same that we demonstrated now before. And also, just for a single step, we can have an exponential advantage also in runtime. And this is because the bond dimension that we need has also converged. This is something that we observe in just one step, but when the number of steps accumulates and we perform the complete evolution, even though we see that the error is the same, so this is MPS and this is vectors, and you can see that the error is the same. So again, same accuracy, even for the complete evolution for MPS and vectors. When it comes to the runtime, now there is no such advantage, and in fact, the MPS is slower in this case. But this is something that has to do not with the techniques, but with the solution or the problem that we are dealing with, because the bond dimension increases with the time. So, and this is more or less, so we perform more complex benchmarks, but the idea is essentially the same. So just to wrap this up, I want to remind you so what we wanted to do, which is to develop quantum and quantum space algorithms for numerical analysis with significant memory compression and time savings while maintaining high accuracy. Here, what we did and the results we obtained, which is highly efficient quantum register encoding, as well as a variational quantum algorithm for solving Hamiltonian PDEs with very nuanced sets for the presentation of functional symmetries. And in the quantum-inspired part, we develop a finite-precision algebra for the development of global algorithms, as well as some accurate approximation of derivatives based on HDAF. All of this is included in a library, which is the CMPs library, that provides an efficient method for developing this kind of MPS in quantum-inspired algorithms. So here you have this in the GitHub and the documentation if you want to check it, all the things that it can do. So it's also useful for like a standard MPS computations, but it has been developed for numerical analysis, so particularly. And just with that, the main conclusion that we have is that this MPS method for the solution of PDEs show this vector when compared to state-of-the-art vector implementations, exponential memory compression, asymptotic time savings, and very high accuracy. And when compared to the quantum algorithms that we have nowadays, they are a better alternative because the NISQ devices are not yet ready for these applications. And with that, just to conclude, in the future, what we would like to do is to keep on working on our CMPS library in order to have a better performance for the library. So we want to accelerate this. One possibility would be to migrate the code, which is Python, to C++. And this has already shown for some preliminary tests 10 times speed up, but we can also include parallelization routines or more efficient spectral methods. And with that, we will be capable of going to higher dimensional problems, or also addressing the effect of noise in some physical settings, or even going beyond that to applications that are not in numerical analysis, such as those in machine learning, especially in the case of optimization. So with that, I conclude the presentation, and now I'm open for any questions. Thank you for your attention.
Cool, thank you very much. It's amazing, very impressive. Wow. I guess now the floor is more open for questions. If anyone has, wow. So maybe I have a first question. This is I know that Luca is in in Pompeu Fabra or UPC in Barcelona, no?
Luca actually is now at CSIC. So some years ago he joined our group.
Ah, so he's in Madrid.
Yeah, so like hybrid.
Okay. Does someone has any question? Otherwise, I have some. But, so maybe to break the ice a bit. Thanks a lot for the talk. I think this is super interesting, and it's like really like maybe. It's like, wow, I mean, if there is any motivation to study physics is and like technology in particular, is like, how do you solve better differential equations? So like, really congrats. I think that the topic of your PhD is really impressive, and I'm a bit jealous that I didn't do the PhD on that. So regarding tensor networks, I heard, and I'm a total outsider, like beyond some talks and discussions with colleagues and whatever, maybe some papers and whatever, but I never worked on this. And I read a bit in the media and stuff that there are like tensor product units. And I wonder, like, regarding hardware, as we talk about GPUs and QPUs, like quantum processing units, is there any hardware in which like tensor products, the tensor networks run more efficient? This maybe has nothing to do with your thesis and your talk, it's just out of curiosity.
Well, yeah, so actually, I mean, I'm not super familiar with this. So we were more, so even though I developed together with my supervisor and some colleagues this library, we were more interested in the application on numerical analysis rather than the efficiency. So we already showed these exponential like advantages, but this implementation could be better for sure. I don't know. In our, I can just say, as far as I know, so in our implementation, the simulations were either run on my computer, but I had like a massive computer with a lot of CPUs and a huge memory. So you cannot really do this in a laptop. So in a lot of the simulations were run on a cluster. We did not use parallelization, but for sure these kind of techniques can benefit from parallelization because there are some steps that can be parallelized. But in our case, these kind of things, in fact, you probably know, so this inclusion of these kind of things will increase like the time, to develop these techniques. This was hard enough as it was. And I also know, I think that there are some libraries, maybe, I think it's QIMP, the one of the Barcelona Supercomputing Center, because I know some people there that are working on tensor networks. And I think that they were trying to use this with GPU, and also I've seen some applications that try with GPU because of these accelerations can also be seen. But regarding like a specific architecture or hardware developed for it, I'm not aware of it now.
Okay,
but it may be.
Yes. Because I think if you use a Google Colab, then you have the option of TPU.
Yeah. So I haven't used it. I mean, I've heard of this, but I'm not like super familiar on how this works. And I know that there are a lot of tensors, so the tensors are used also in machine learning and things like that. But it does not mean that it is a tensor network, so it could be other things. So that's why I'm not super aware on how this is related to tensor networks, or if they could be benefit from these architectures.
I think a TPU is, well, what they call a TPU is just a gimmick because it's a GPU with less floating point precision, so it can go faster, but it's like a GPU in essence, I think.
Okay. Yeah, it makes sense then.
Okay, interesting. Anyone else has questions?
Well, me, more than a question. First of all, thank you very much, Paula, for the excellent presentation. I'm really looking forward to continue the conversations. I think that one of the lines of research that you presented is to extend the framework to non-Hamiltonian functions and to other frameworks of work. Did you have anyone particular in your mind, or any specific? Because now I don't know. There are different problems that are happening now that are specifically related not to the quantum space, but also from the classical perspective in which potentially this could be applied. Do you have any favorite? Let's say line to go on.
Yeah, for me, so we focus on these Hamiltonian PDEs, even though we did both static and independent, but we're all Hamiltonian, but these techniques are not exclusive of this. And in fact, like in the literature, you can see like a lot of applications nowadays. So this is becoming a more and more popular research field. And one of the things that I feel that is super interesting, and I see a lot of people working on that, so maybe this could be interesting to try as well for me, is to research into the Navier-Stokes equation and all these fluid dynamics applications in general. So there are a lot of groups that are making a huge effort to develop these methods in this area, because these fluid simulations is super hard in practical applications. You need a lot of memory, and they have seen that with these kind of techniques, they can obtain also very interesting results. And these are also more complex because they are non-linear equations. We have focused also on linear, but the extension to non-linear is quite simple for this MPS, not so much for the quantum algorithm case. Yeah, I think this would be an interesting way of continuing with that. Other alternatives that I actually tried, but we did not continue because, I mean, the time of a PhD is limited. Other alternative was to study source PDEs, for example, the heat equation. I believe these kind of things are also being studied in this context of tensor networks, because one of the applications that is very interesting nowadays is finance. And one of the models that is widely studied is the Black-Scholes equation for option pricing, which in turn can be rewritten as a heat equation. And I have also seen tensor network works for solving this kind of PDE.
Yeah, I'm thinking also the possibility of using that for some of the fusion models on generative models probably as well. This could be also an option.
Yeah, sure.
Very, very interesting. So thank you very much, Paula.
For fluid dynamics, I think it is the state of the art, or at least I mean, I know people working in. You mentioned La Torre, no? That he's in Arabia Saudita or whatever in the Technology Innovation Institute, and there is a subgroup there that works with tensor networks, no? And I mean, I remember they were presenting their results as a state of the art in fluid dynamic simulation, which I find like absolutely impressive. I don't know if it's
so for me, this is another.
Not.
Yeah, there's another person that is like a real expert on this, or is working a lot on this area. It's also Michael Lubash. Michael,
the Russian guy.
No, Lubash is German, but he works at Quantinuum in London, and he, together with some collaborators like Dieter Jacks or other people that are working on that, his student, I think it was Nikita Guryanov, something like that. They have like different research on how to do this with techniques based on DMRG for different settings within this fluid dynamics of area. So also very interesting. I will have to check this one of the La Torres group, which also seems very nice.
I don't know if we want to keep with questions, and maybe we are a bit tired and whatever. I feel it's super cool, the presentation. Maybe I want to do one more question, please.
Yeah, sure.
Which is like, I don't finish understanding, like, so you presented this line of, like in the first part of the talk, you were showing the quantum harmonic oscillator, no? And this is a bit more a conceptual thing, no? Instead of doing, I don't know, like using the quantum computer for quantum simulation or dynamical simulation, no? Like you leave the computer, you prepare the state, no? You have the Hamiltonian that you make it artificial or whatever, like you simulate the quantum harmonic Hamiltonian, no? Digitally, and then you let the computer that evolves in time, and then you infer the quantum state and the solution. You are doing this, but routing like you are encoding. You want to do this classically, mapping quantum, and then back again to classical, no? And this is very particular because you are using the quantum harmonic oscillator. But in principle, you could have, I don't know, the classical harmonic oscillator with the quantum encoding. Is this correct?
Yeah. So in this context, so you have to be capable of representing the operators of your Hamiltonian or your PDE, whatever, in the form of in this representation. So this is not always possible because you need to use this binary encoding, but so it would depend actually on the exact form of the thing that you want to encode. But we could try other things, yes. So in this case, this was just used for these quantum circuits, which are qubits, in fact. But yeah, this could be, we could try other kind of things, I think. I mean, also depends on the form of the solution, because you are restricted to these highly smooth and differentiable functions, but this is in fact not such a big restriction because a lot of functions in this numerical analysis have this kind of behavior.
Okay. And then I have another, like, because for this particular set of problems, like you have like a continuous variable problem, no? Like you have the harmonic oscillator, no? And then you want to solve it digitally using all these digital in the sense that you want to use it with solve it with qubits, right? And with quantum circuits. In principle, to map this, you need to map from bosons to qubits, no? And then back again, and you use these transformations. Do these transformations you somehow surpass all this, no?
Yeah, because so you are representing this as a grid. So it's the same kind of discretization that you will do for a standard numerical analysis. So you do not need to go past this kind of particle representation. So you just encode the amplitudes, the differential values in the amplitudes. Yeah.
Okay.
Okay. Sorry, I have to go now because they're waiting for me. No.
Okay.
Yeah, no, deadly interesting. I don't have anything to ask, especially because I spent a bit of time on just non-Hamiltonian equation for a while. So basically, I don't have anything special to see. Maybe looking forward for your progress. So good luck. And that's why I was asking you if you ever considered traditional polynomial or other stuff. They usually done, for example, in fluid dynamics. I've seen some articles. They use the spectrals and they implement inside that. Now it is in VQE recently. This kind of things. This is just like 2 cents. And I'm sorry, but I'm already late. Thank you very much.
Okay. Thank you for coming.
Bye.
I
Well,
think it is.
thank you. I think that we will, in any case, we will have definitely. We spent a while speaking about differential equations and quantum formulation and tensor network. Thank you very much for your time. In any case, Paula, and I'm really looking forward to continue the conversation. Thank you, Matthias, for organizing it.
Thank you. Thank you very much.
Yeah, thank you for inviting me.
Definitely, we are in touch. I stop recording, right? Okay.